Welcome friends on the topic of ordinary differential equations in the paper of numerical methods and the subject of information technology in EPG Pathshala. Today we will begin our journey for studying numerical methods to solve ordinary differential equations. Initially, to study numerical methods for solving ordinary differential equations, we will hurriedly revise the concepts of ordinary differential equations needed to apply numerical methods to solve ordinary differential equations. So, we will go through the preliminaries and then we will take a particular type of differential equations which are called initial value problems, and we will learn about the different numerical methods which exist to solve initial value problem. And out of these numerical methods, in today's module, we would be able to cover the Euler method, which is one particular case of general Taylor series method. So, we will study the concept of the Taylor series method and the particular case of Taylor series method, which is known as Euler method. So, let us begin. First, let us begin with what is the importance of a differential equation, because that will give us the idea how important it is, how crucial role it plays in today's world. Though in your undergraduate and postgraduate studies, you would have already had a paper on the different analytical methods to solve differential equation. See, in all scientific engineering cases, any discipline you name it, health, medicine, economic, whenever the mathematical modeling is done of these problems, many times they give rise to so called differential equations which need to be solved to get a solution of the problem. To give you a brief idea, let us take the simplest example possible, and that is about the population prediction in future. You very well know every 10 years the census is taken and the table is made of the current population of a country. See, many things depend upon the estimated population, how much consumption would be there, how much sales would be there, what import would be needed. So, lot of planning, all the requirements has to go with the status of population. Just to have a very simple model, let us say we know the current population and we want to predict what the population would be in the future. We need to know the current population and also we need to know at what rate the population is changing. So, if we denote the population by P, let us say, we denote the population by P, and the rate of change of population with respect to T is dP by dt, derivative of P with respect to time T. And this rate of change is proportional to the population P. So, we can say that T p by dt is given by k times P, where k is a constant. And solution of this differential equation, this is a very simple differential equation and arises in many growth problems. So, differential equation has a solution. Population P at the time T is given by C is a constant into e raised to T, where T is time. Just to simplify the matters, if population at 0 is 100, then if you substitute P0 is 100, put T equal to 0 in the expression Pt equal to C e raised to T, then P0 is 100. So, we get C into e raised to 0 is 100. So, C e raised to 0 is 1, we get the value of constant C as 100, and so we can say the solution of this differential equation, if the current population is 100 units, P is given by 100 into e raised to T. And so, if you want to estimate the population at 2 years hence, we will put T equal to 2 if T is measured in years, and we will get the population as 100 into E square. So, this is the example of a very simple differential equation which I have shown you is needed to be solved to get a particular solution. So, now let us understand first of all how do we define a differential equation. You see, a differential equation is an equation which connects independent variable x, let us say, a dependent variable y which is a function of x, depends upon the value of x, and its derivatives. So, an equation involving independent variable, dependent variable and its one or more derivatives is called a differential equation. Some well known simple examples of differential equations are y double dash plus 4y equal to 0. Y is a function of x, but for simplicity we do not write y x, it is understood. dy by dx we denote by y dash, second order derivative d2y by dx to denote it as y double dash. General dn y by dx and another derivative of y with respect to x is denoted by yn and so on. So, these are very simple, very classroom examples of differential equation. Y double dash plus 4y equal to 0, y x plus y dash plus 1 by y is 0, or y double dash minus 2 y dash plus y equal to 0. So, once we have understood what a differential equation is, the second thing which we need to understand is what is meant by a solution of a differential equation. Now, we know that differential equations arise while solving scientific, engineering, economic, business problems. Now, when we have to solve a differential equation, we need to understand what is meant by solution of that differential equation. A solution of a differential equation is the function y, function of x, which satisfies that differential equation. Like for example, if we take the differential equation which I had cited just now, second derivative of y with respect to x plus 4y equal to 0, has a solution y is given by c1 into cos 2x plus c2 into sin 2x, where c1 and c2 are arbitrary constants. See, always the solution of a differential equation is a curve, is a function, so it is a curve. And since you know we have already done the module on the integration, after all solution of the differential equation involves integration. So, as many derivative, power of derivative is involved, those many constants we get in the solution, and so the solution is not unique. Whatever be the C1 and C2, depending upon, we will get the solution. So, C1 and C2 are arbitrary constants. If we want to verify, say this is a solution, we want to verify it is a solution, we are it is very simple, differentiate y, because we want to see that this y fits that equation. So, y, the equation is y double dash plus 4y equal to 0, y is given by this function. So, differentiate y with respect to x. So, y dash is c1 as it is, derivative of cos we know is minus, it is a function of a function cos of 2x. So, derivative of cos minus sin 2x and derivative of 2x is 2. So, we get y dash x is minus 2 c1 sin 2x plus second term is c2 sin 2x. So, c2 into derivative of sin is cos. So, cos 2x into derivative of 2x, so that is 2. So, first derivative dy by dx is given by minus 2 c1 sin 2x plus 2 c2 cos 2x. Our differential equation involves second derivative of y, y double dash plus 4y equal to 0. So, let us differentiate this y dash once more. So, when we differentiate this y dash once more, y double dash x is minus 2 as it is, c1 there is a constant multiplicator, they remain as it is. So, minus 2 c1 into derivative of sin 2x, sin 2x derivative is 2 cos 2x. So, we get minus 4 c1 cos 2x plus 2 c2 into derivative of cos 2x, that is minus 2 sin 2x. So, we get minus 4 c2 sin 2x. Here you take minus 4 common, inside the bracket we are left with c1 cos 2x plus c2 sin 2x, that is yx. So, we get y double dash x is minus 4y, take minus 4y on the left side, giving us y double dash plus 4y equal to 0. So, verification that a particular function is a solution of a differential equation is very easy. Just differentiate and see that those derivatives satisfy the differential equation. So, similarly, we can see that the solution of y double dash minus 2 y dash plus y equal to 0 is given by y equal to c1 e raised to x plus c2 x e raised to x. All one would need is differentiate y with respect to x, form the equation y dash, again differentiate y double dash and substitute those expressions in the left side, that is y double dash minus 2 y dash plus y, and you should get the result to be equal to 0. All terms should cancel. And similarly, it can be verified, this is all left as an exercise for you. So, y equal to 2 times square root of c minus x. Here the equation has only first order derivative. So, there is only one constant c here. So, y dash plus 1 y equal to 0 is satisfied by y equal to 2 times square root of c minus x. Now, see, if there is only one independent variable, the derivatives involved in the equation are ordinary derivatives, and such differential equation is called ordinary differential equation. So, when dependent variable is a function of only one variable, then all the derivatives involved in the equation are ordinary, and the equation is called ordinary differential equation. If dependent variable y is a function of more than one independent variable, maybe 2 variables, 3 variables, a function of several variables, in that case we get partial derivatives in the equation. If u is a function of, let us say, 2 variables x and y, so we get derivative of u with respect to x treating y constant, that is called partial derivative of u with respect to x, denoted as curly u by curly x, delta notation. And similarly, treating y as a variable and treating x as constant, we get the derivative of u with respect to y, denoted as curly u by curly y. So, these are partial derivatives. Similarly, we get second order partial derivatives, third order, so on. So, whenever a particular dependent variable is depending upon more than one variable, the equation contains partial derivatives, and such differential equation is called partial differential equation. They are very famous partial differential equations which are known as elliptic equations, namely Laplace differential equation and Poisson differential equation. See, the Laplace equation is curly 2 u by curly x2 plus curly 2 u by curly y2 equal to 0. So, curly 2 u by curly x2 is derived how? U is a function of x and y. So, you differentiate u 2 times with respect to x as if y is a constant, and similarly curly 2 u by curly y2 will be obtained by differentiating u with respect to y treating x as constant. And Poisson equation is curly 2 u by curly x2 plus curly 2 u by curly y2 is equal to function of x y. The methods for solving partial differential equations are different than from the methods for solving ordinary differential equations. So, we are going to focus on the numerical methods to solve ordinary differential equations. So, let us go ahead. Once we have understood the solution of an ordinary differential equation and it involves arbitrary constants. Now, you know that in the case of numerical methods, we can obtain numerical answer to a problem. We do not obtain analytical solutions, and moreover the problem should be a particular problem. The solution cannot contain arbitrary parameters. But luckily, in all these scientific engineering problems, always the differential equation which arises is accompanied by auxiliary conditions. So, once we combine these auxiliary conditions with the differential equation, we are able to obtain a particular solution, a unique solution to a differential equation. For example, if we take the differential equation y double dash plus 4 y equal to 0, and if the conditions, see there are two constants, we need two conditions, y 0 equal to 1 and if the derivative is equal to 2, then the particular solution of this equation is given by cos 2x plus sin 2x. Let us see how it is given by. See, y is c1 cos 2x plus c2 sin 2x. Now, we want to determine the constant c1 and c2. we want to find the values of C1 and C2, and we are given two conditions, namely y0 is equal to 1 and y dash 0 is equal to 2. So, we will differentiate y with respect to x, get y dash, and in these two expressions we will substitute x equal to 0, y x equal to 0, because we are given the value of y at 0 and the value of derivative of y at 0. So, we get y0 is 1, we substitute. So, we get C1 cos 0 plus C2 sin 0, and that should be 1. See, sin 0 is 0 and cos 0 is 1. So, we get the answer 1 is equal to C1, gives us the value of C1. We differentiate y with respect to x. So, y dash x is minus 2 C1 sin 2x plus 2 C2 cos 2x. In this we put x equal to 0 to get the value of derivative at x equal to 0. So, y dash 0 is 2. So, we get minus 2 C1 sin 0 plus 2 C2 cos 0 is 2 and cos 0 is 1 and sin 0 is 0. So, first term becomes 0. We get 2 C2 into 1 is 2, giving us C2 is 1, and so the solution is given by yx is equal to cos 2x plus sin 2x. So, this is how you can see that y dash plus 1 by y equal to 0 will have a unique solution given by 2 times square root 1 minus x, and y double dash minus 2 y dash plus y equal to 0 will have a unique solution given by e raised to x plus x e raised to x if the conditions given are y0 is 1 and y1 is equal to 2e. So, we have learned that how to get a unique solution of a differential equation. Now, the next thing is that these conditions which are given, the extra conditions which are given, these conditions may be given at a unique point, which may be our starting point, or may be given at different points. If these extra auxiliary conditions are given at different points, then the differential equation is known as boundary value problem. Whereas, if the extra conditions are given at the unique point, then these problems are given called as initial value problem. For example, if you look at the table here on the slide, y double dash plus 4 y equal to 0, if y0 is 0 and y dash 0 is 2. So, here these two conditions are given at the same point x equal to 0. And so, this differential equation combined with these two conditions given to us will be called an initial value problem. Second, if you look at y dash plus 1 by y equal to 0, it is first order differential equation, y0 is 2, condition is given at the one point. So, this is also an example of initial value problem. Let us look at the third equation in the table, y double dash minus 2 y dash plus y equal to 0. Here in the solution there are two constants, we need two conditions. So, two conditions are y0 is 1 and y1 is 2e. Here the conditions are given at two different points, namely at 0 and 1, and so this differential equation combined with these two conditions will be called a boundary value problem. With this, now let us also revise what is meant by order of a differential equation and what is meant by degree of a differential equation. See, the order of a differential equation is the order of the highest order derivative present in the differential equation, whereas degree of a differential equation is the power of the highest order derivative. Mind it, power of the highest order derivative present in the differential equation, provided that differential equation is a polynomial in the derivatives of y. Again, let us look at the examples cited in the table one by one. First example is y double dash plus 9y is e raised to x, and same in that row we have taken second example y double dash minus 2y dash plus y equal to 0. Both these differential equations, see, they have the highest order derivative as second order y double dash. So, the order of these two differential equations is 2. Look at the second row, y dash is the highest order derivative is first. So, order of the differential equation is 1. In the third row, we have 5y triple dash plus x square y double dash cube plus y dash square is 5y plus x. Here highest order derivative is the third order y triple dash. So, the order of this third differential equation is 3, and lastly fourth row y double dash plus x y square plus e raised to y square is 0. It is second order derivative is present. So, order of this equation is 2. Again, now let us look at degrees of these differential equations one by one. Again, let us look at the first row. Here order is 2, so look at that term. So, y double dash power is 1 in both of them. So, degree of both these differential equations is 1. So, they are second order first degree differential equations. In the second row order is 1 and power is also of y dash 1. So, it is first order first degree differential equation. In third it is y triple dash, that is a third degree third order sorry, and the power is 1 of the highest order derivative, namely 3. So, degree is going to be 1. Do not get carried away by the power 3 of y double dash, because order is 3, highest order derivative is y triple 3 d 3 y by dx 3 and its power is 1. So, degree is going to be 1. Look at the last row y double dash plus x y square plus e raised to y dash equal to 0. In this differential equation order is 2, but what about degree? See, this differential equation is not a polynomial in the derivatives of y, and as a result this degree of this differential equation is not defined. So, briefly we have revised what is a differential equation, what are their importance, what is mean by order and degree of a differential equation, what is mean by solution of a differential equation, how we verify whether a given function is a solution of differential equation, and how do we get numerical differential equation, how do we solve by numerical methods, we will just see. So, we today are going to focus on first order differential equations, and they are known as initial value problem. So, form of an initial value problem is dy by dx is equal to f x y, and we need one condition. So, y at the point let us say x 0 equal to y 0, and we need to solve this differential equation let us say on the interval a to b, because in numerical method when we will apply this solution, when we will find a solution using numerical methods, see we will get a solution on an at certain points. We do not get answer in the form of a function. So, we will get the values of y. So, we find y at certain points. So, we find a solution on a particular interval, we do not get the solution in the form of a general equation. So, solution of an initial value problem is to find y x if we satisfy this differential equation. Before we proceed to numerical methods, the question arises whether given initial value problem has a solution, whether it has a unique solution, and whether the solution is stable, meaning how sensitive the solution is to the coefficients involved in the equations. The analytical mathematics behind this says that if f satisfies Lipschitz condition on a particular region which contains the initial point x 0 y 0, then the differential equation is well posed and is stable. Those who are interested in studying about the Lipschitz condition, they can refer the books Ralston, Brady and other books which are specified, and they can study in detail what Lipschitz condition is. You would like to ask again that so many thick books exist, so many analytical methods exist. I am very sure under undergrad courses you would have studied one full paper on methods of solving differential equations, then why do we need to go for numerical methods? And again, see, analytical methods exist, many times they are unimaginative, unintuitive. So many methods exist, so it becomes difficult to select which method would be used, which method would be applicable to solve a given differential equation. Secondly, many times the differential equations do not have analytical solution also, or the form of analytical solution is in the form of an infinite series, and again you need to approximate that infinite series to get the value of function at certain points. Many times the functions involved may be too complex to be able to apply analytical methods to solve them, and therefore, again we definitely need to study the numerical methods to solve a given differential equation. Let us understand what is the nature of numerical methods to solve a differential equation. What is done in the numerical solution is, if we need a solution over the interval a to b, let us say, our starting point is a, we will call it x 0. We divide the interval a b into n equal parts. Our step size h is b minus a by n, and we will find the solution at the point beginning point x 0 is given to us, initial value problem. We will find the value at the point x equal to x 1, then at the point x equal to x 2, then at the point x equal to x 3. So, step by step beginning from x 0 at x 1, at x 2, at x 3, at x 4, and so on we go up to x equal to x n at the point x equal to b. So, this is how we proceed to solve the differential equation. And what is the behavior of the formulas? How do we solve it? See, we are given at the initial point x 0 value of y at the point a, that is we are calling it as x 0. We are given the value y at the point x 0 is y 0. How to get the value at the point x equal to x 1, that is x 0 plus h? We will call the value of y at the point x 1 as, for simplification purpose, as y 1. So, y 1 will be obtained from the value of y at the point x equal to x 0 as in the terms of function value, because dy by dx is f x 0 f x y. So, using this function f and the value at the point x 0, that is y 0, this is how we will determine y 1. Then how will y 2 be obtained? Y 2 will be obtained from y 1, may be possibly y 0 also may be used, and the nature of function f. So, this is how we go on. Y at x 3 will be estimated from y 2, y 1, possibly y 0, and definitely the function f. And we stop when we reach the point b, that is we get the value of y at the point x n, and that is the value of y at the point x equal to b. If it is computed, we stop the procedure. So, we obtained the value of function y at discrete set of points x 0, x 1, x 2, x 0 it is given, x 1, x 2, x 3, x n minus 1, x n, we get these points. And if one is interested in knowing the curve, one can, using these points, they are quite nearby points, one can plot the curve, and maybe using interpolating technique or any other technique can be used to plot the curve and get the curve. Now, the methods to solve ordinary differential equations are classified into two categories, one which are called single step methods and other which are called multi-step methods. The single step methods have the characteristics that they are direct methods, meaning by you have a formula where you substitute the values and you get the values. So, they are not iterative in nature, you apply once and you get the estimate. As a result of their directness, they are not iterative, you cannot estimate the accuracy in them, because there is no idea. Whatever accuracy estimate you have is on the basis of the formula, on the basis of analytical formula, on the basis of truncation error formula, we can have an idea about what the error would be, but we cannot compare using, because if the method is iterative, we can compare the new value with the previous value, we have the idea of the sequence of the approximate solutions. So, since they are direct, that estimate cannot be computed except from the theoretical formula. And all these single step methods are based on Taylor series method, and the method of course is they use the value of their single step. So, they use the value of estimated value of y at the previous step. So, y1 will use the value of y0, y2 will use the value of y1, y3 will use the value of y2. So, only one single step. So, only one previous step value of function and the nature of function f that would be used to estimate the value of y. The other category of method of solution of the differential numerical methods are called multi-step methods. So, let us look at the characteristic of the multi-step methods. As the name is multi-step methods, they use more than one previous step, the value of function at more than one previous step to compute the value at the current step. And many of them, not all, but many of them are iterative in nature. And because those of them which are iterative, you can have an idea about, practically you can have an idea of how much accuracy we are achieving. Obviously, because they use the more than one previous step, they will not be self-starting. Like suppose a method, multi-step method uses the result of 3 previous steps or 4 previous steps. So, in order to compute y4, I need the value of y0, y1, y2 and y3. So, y at x4 can be calculated using the values y at x0, y at x1, y at x2 and y at x3. How do we get these values? So, we need to have from some other method the values generated, maybe single step methods, to have values generated at x1, at x2 and x3, and then only the multi step methods can be started. So, they are not self starting methods, but they are iterative. So, you can have an idea of the accuracy. Many of these multi-step methods are under the category of what are called predictor corrector methods. In the case of predictor corrector methods, you have two formulas, one which is called predictor, so which predicts the value of y, and the other which is called corrector. Corrector is an iterative formula, you go on applying it again and again, which corrects the values of y till you get almost results which are correct to certain number of significant digits or decimal places as need be. So, with this let us come to what is known as Taylor series method, because now we are first focusing on the single step methods. Today we will begin our journey on the single step methods, and these single step method we will also continue in the next module, and maybe my third module on the ordinary differential equation would be able to cover the methods which come under multi-step methods, and namely predictor corrector methods we would be tackling. So, to begin our journey with single step methods, as I pointed out in my earlier slide that all of them are based on Taylor series method. So, let us briefly review what a Taylor series method is. Later on in my next module, we will take up in detail working with the Taylor series method. The Taylor series method is, theoretically you can obtain the solution up to any desired accuracy. It is a backbone, spinal cord of these single step methods. On its own, it is not much of practical use, for the simple reason that this involves partial derivatives of f x y. So, any particular IVP to be solved, any particular initial value problem to be solved, one has to compute the partial derivatives first before programming, before implementing, and that is why practically on its own it is not much of practical use, but as I said, it is backbone of all the direct single step formulas. There is a family of formulas which are called Runge-Kutta formulas, they all are based on the Taylor series, and Euler formula is the first in the family. It can be called Taylor series method of order 1, it can be also called first order Runge-Kutta formula. Today we are going to study in great detail what is this Euler formula, but before that let us learn the concept of the Taylor series method. Already we know that the Taylor series, let us say y is a function of x, will be given by, if we expand y x in Taylor series in powers of x minus x I about the point x equal to x I. general x equal to xi. See, our xi I is 0 will get x 0. So, power of x minus x 0 when we are estimating y at x 1. When we are estimating y at x 2, we are expanding in the powers of x minus x 1. So, general when we are expanding about the in the powers of x minus xi about xi, this Taylor series is given by yx is yi, that is y at the point xi, plus x minus xi into first order derivative of y at the point xi, plus next term is x minus xi square by 2 factorial, second order derivative of y at the point xi, next term is x minus xi cube by 3 factorial, third order derivative at the point xi, plus so on up to nth power x minus xi is to n by n factorial, nth derivative at the point xi, and then the remainder term. If I put in this x equal to xi plus h, we ignore the remainder term and we put xi plus 1, x equal to xi plus 1 on the left side, and on the right side also I put x equal to xi plus 1. So, this expression becomes the xi, x takes the role of x, x is xi plus 1. So, xi plus 1 minus xi becomes h. So, doing this it gives us yi plus 1 is yi plus h yi dash plus h square by 2 factorial yi double dash and so on. Now, see, the concept is retain as many terms as you feel good, h is going to be small, and ignore higher degree terms. So, I may decide to retain only first order term or maybe second order term or maybe third order term, ignore the higher terms, and those the right side terms are used to estimate yi plus 1. See, yi plus 1 you get in terms of yi and derivatives of y. So, or derivatives of y at the point x equal to xi. So, retaining up to certain number of terms gives rise to different methods. Let us take the simplest case, and which is known as Euler formula. It is also called Taylor's formula, Taylor's method of order 1. Basically, in this method we are only keeping terms up to power of h and ignoring second and higher degree terms. So, our n is 1. So, in this our Taylor series, the previous Taylor series, h square by 2 factorial onwards the terms are going to be ignored. So, what we are left with yi plus 1 is yi plus h yi dash, and our yi dash is what? dy by dx is f x y. So, yi dash is f at the point xi yi. So, our Euler formula becomes yi plus 1 is equal to yi plus h into f x y yi, a very simple formula, the simplest it is possible. Before we proceed to solve and apply it, let us understand the geometrical meaning of this method. See, tangent, what is y dash x? It is the derivative of y. Graphically, it stands for slope of tangent to the curve at the point x. If we draw the tangent, the straight line tangent to the curve y equal to yx at the point x, xi yi, the equation of tangent will be given by y, it is passing, it is at the point xi yi. So, it is y minus yi equal to m is the slope of the tangent, which is yi dash into x minus xi. So, it is the equation of straight line passing through xi yi having slope yi dash. And if in this straight line, if I put x equal to xi plus 1, I am estimating the point, the y value of the point on this tangent, which is drawn to the curve at the point xi yi. So, I put x equal to xi plus 1. So, right side becomes y minus yi is yi dash into h, and yi if I take on the right side, it is yi plus h yi dash. So, we are actually estimating, and this is the estimate of yi plus 1. So, basically we are estimating the value of x, value of function, the solution function at x equal to xi plus 1 as a point drawn on, as a point on the tangent line drawn to the curve at the point xi yi. Let us look at the graph. x axis, we are drawing y axis. Let us say this is the curve y equal to y x. At x 0, the function value is y equal to y 0. We have drawn the tangent to the curve y equal to y x, which is the straight line given by y equal to y 0 plus y 0 dash into x minus x 0. At the point x 1, we are estimating the value of point y 1 as a point on the tangent line, but actually the point is on the curve, and you can see the error. This much is the error, truncation error, which is occurring in the estimate of y at the point x equal to x 1 due to ignoring the second and higher degree terms. See, now in the case of differential equation, when we proceed ahead, because now x 1 estimate contains the error, so y 1 has the error. So, when we estimate y 2 from y 1, that also has that error gets compounded. When we estimate y 3, the error in y 0 and y 1 will get compounded. So, this is what happens. This is just shows the diagram x 0 y 0, draw the tangent. At x 1 we are estimating through, we get the value at x 1 y 1, and then again we are drawing estimated to curve f x 1 y 1 drawn tangent, we estimate y 2, same way we estimate y 3, and the amount of error goes on increasing. So, which is known as global truncation error in the case of differential equation, because globally as we proceed to the points, as we go on, the truncation error goes on increasing, because all next future points are inheriting the errors from the previous points. Now, let us look at the two illustrations, two simple illustrations. First differential equation, dy by dx is x minus y, y at 0 is minus 2, let us take, and let us take the step size h equal to 0.1. So, what does this mean? This means we will begin at x equal to 0, y 0 is minus 2, we will get apply the formula y I plus 1 is y I plus h f x I y I. F x y is x minus y. So, y I plus 1 is y I plus h into x I minus y I. So, y 1 will be estimated, x 0 is 0 and y 0 is minus 2. So, y 1 is, if we simplify the formula, y I plus 1 is 0.1 x I plus y I minus 0.1 y I, that gives 0.9 y I. So, y 1 is 0.1 x 0 plus 0.9 y 0, x 0 is 0 and y 0 is minus 2, substitute 0.1 into 0 plus 0.9 into minus 2. So, answer is minus 1.8. This is our estimate for at value of y at x equal to 0.1. Again apply the formula to calculate y 2, y 2 will be y 1 plus 0.1 into x 1 minus y 1. So, 0.1 x 1 plus 0.9 y 1, and we get the answer 0.1 into 0.1, x 1 is 0.1 now, plus 0.9, y 1 is estimated to be minus 1.8, substitute and we get the answer minus 1.61. Now, we know the solution of this differential equation. You can verify that solution of this differential equation is given by x minus e raised to minus x minus 1. Now, pseudocode I have given in the e text, we apply the program, we run it with the following tables show you the results with the different step sizes. If you look at h equal to 0.2, the exact solution is given by minus 0.3676790. At x equal to 1, approximate solution is minus 0.3276890. So, we get the absolute error and the percentage relative error, which is of the order of almost 11%. If we reduce the step size, h is 0.1, see the error is of the order of h square, we have ignored h square terms. So, expect that the absolute error should decrease and it should result in decreasing of percentage relative error also, and that is what happens at x equal to 1, absolute error has become 0.019210 and percentage relative error has decreased to 5.21. It has almost become half, from 11% to 5.2% by reducing the step size to be half. See, as such the error is of the order of h square, but what happens is, because when we are adding and globally due to global truncation error, basically it is the error reduces only by the order of h. Further, h step size also become further half, h equal to 0.05, and the tables has been made. And again, if you look at the last row solution at x equal to 1, the relative error has become now 2.35%. So, it has further reduced. So, this is the table which shows the comparison of the error with the different step sizes. With this particular example which we have taken, exact value is minus 0.36788790, and see the approximate solution for 0.2 step was minus 0.33, 0.1 it was minus 0.35, 0.05 it has become minus 0.35. The absolute error has gone on decreasing from 0.04 to 0.009, and percentage relative error has decreased from 10.92% to 5.21% to 2.5%. Similarly, let us take another example. Dy by dx is x upon y, y0 is 1, and again we repeat the same exercise as x0 is 0, y0 is 1, fxy is x upon y. So, apply the formula yi plus 1 is yi plus h into f of xi yi, and go ahead. So, and we again we have drawn the table. Correct solution is given by square root of x square plus 1, and we have tabulated the results obtained with h equal to 1, h equal to 0.5, h equal to 0.25 and h equal to 0.125. I advise you all to run the write your program or use any package if you want, Maple or Mathematica or MATLAB, or write a program if you have no a programming language, and run these programs, verify these results. So, if we again compare the truncation error with different step sizes 1, 0.5, 0.25 and 0.125, see the approximate solution, initially we got 5, then 5.036, then 5.066, then 5.08, with the absolute error as 0.099 to 0.062, then 0.032, then 0.0166. So, percentage relative error decreased from 1.94 to 0.32%. So, the reduction as expected, truncation error, if you reduce the step size, the truncation error will decrease. So, in summary, what we have learned is that differential equations are very important. We need to learn numerical methods to solve differential equations. We learned that there are two categories of methods to solve first order differential equations called initial value problems, namely single step formulas and multi step formulas. We began our journey with the single step formulas. We also realized that Taylor series method is the backbone of all the single step methods, and in particular we learned the first in the series of the Taylor series method known as Euler formula. We understood this method graphically, also saw the truncation error by taking two particular examples, that truncation error decreases with the step size, with the truncation error decreases with the decrease in the step size, and also we saw that the global error in the case of Euler formula is of the order of h, because as we proceed the errors are inherited and we get the error, global error of the order of h. So, once again thank you very much for visiting EPG Pathshala, and when in next module we will learn the other methods, other family of methods which are known as Runge-Kutta formulas. Again they are, all those formulas are derived from the Taylor series methods only, but the advantage of those formulas are that we do not have to evaluate the partial derivatives. The equations are derived, so that only function evaluations are to be used in those formulas to get the estimate of the value of y at discrete data points on the desired interval. So, thank you very much. Thank you for visiting EPG Pathshala. Wish you all happy learning.